So based off of the energy equation we learned previously, now we're going to look at slightly more complicated examples of these problems. And these are problems involving calorimeters. So a calorimeter is a device that's used to measure heat or energy given off or absorbed by a reaction or a process. If it's not a chemical reaction, if it's some sort of physical change that releases or absorbs heat, you can use it as well. It's important to realize that calorimeters contain water. So you use the mass of the water and the temperature change of the water to determine the energy change of the water. But of course, the point of a calorimeter is not to find out about water, it's to find out about the food substance or whatever substance you put inside the calorimeter. So let's just pause for a moment and look at what a calorimeter is. Okay, a calorimeter should be some sort of insulated device. It can be just kind of a fancy beaker, really, where you can insert a thermometer and have water surrounding a chemical reaction, because it's hard to put a thermometer onto the chemicals that are reacting, because quite often the chemicals totally change. So you might be able to tape a thermometer onto a block of iron, but if you're doing a chemical reaction with the iron, it's not going to be a solid iron anymore. It might become a fine powder like rust. So instead of trying to put the thermometer on the chemicals themselves, we're putting the thermometer in the water and measuring temperature changes that way. So in these kind of bomb calorimeters, we can have a food sample inside of a reaction chamber where we can provide plenty of oxygen. We can ignite the food sample, see how much heat is given off, and measure the heat that's given off by measuring the temperature change that occurs inside this water surrounding the reaction chamber. Of course, in a chemistry lab, we may not have a fancy bomb calorimeter like you see here. We may be trying to do measure the temperature change in a less sophisticated device, and so quite often we'll have a beaker of water that we're trying to heat, maybe by burning different substances below that can of water. Of course, without the insulation, obviously heat can be lost to the environment. So this is a much less precise method than what you would use in a food technology lab. Okay, so we've got this water. We're using the mass of the water and the temperature change of the water to find out what's happening to the water. Why does the temperature of the water change? Because you've done some sort of chemical reaction inside of the calorimeter or outside of the calorimeter, as you see in this picture. And you're looking to see how that chemical reaction or physical change affects the temperature of the water. So you can ignite the food inside of the calorimeter or mix two chemicals together and see how much heat is given off. If the reaction is exothermic, if it releases heat, Q is negative. We said that before, that an exothermic reaction, Q is negative. But the water absorbs that heat. The water absorbs that heat. That's a positive Q process. That's an endothermic process. Thinking about things in the opposite direction. If a reaction absorbs heat, it's endothermic. So Q is positive, according to the definitions we've learned before. But the water is releasing heat. So the water has undergone an exothermic process where Q is negative. So whatever happens to the water, the opposite change has happened to the reaction mixture that you've put inside the calorimeter. This is an example of conservation of energy. However, whatever the energy change you observe in the water, there was an equal and opposite change in the chemicals that you were investigating. So if you were burning food, there's an equal and opposite change in energy in that food that you've burned. And we can use this property, this conservation of energy, an equal but opposite change. And by opposite, I just mean negative. Notice that the energy change of the water is equal to the opposite sign of the energy change of the substance. We can use this to figure out how many calories are in a particular food product. So let's do an example problem like that, where you're taking your favorite blended iced coffee beverage from your coffee shop of choice. You need to dehydrate it first, because with all that water there, we're not going to be able to ignite it, catch it on fire. So we're going to dehydrate it. So you're going to put the beverage that was originally about 6 ounces, 170 grams, and put it into a bomb calorimeter and ignite it. The calorimeter contains 100 grams of water. If the temperature of the water rises from 21.5 degrees Celsius to 81.4 degrees Celsius, what was the energy released by burning the drink? So we have an initial temperature, a final temperature. We know the mass of the water. This is a distracting piece of information. We don't need it for the purposes of this experiment, for this calculation, because we are looking at the energy change involved with the water. So it doesn't matter how much coffee drink that we started with. If we wanted to know the energy change per gram, we would use this information, but we don't need it for this problem. We are trying to calculate the energy released, so that's the joules, and the piece of information that isn't given to me here is the specific heat capacity of water, but hopefully by now you know that that value is 4.184 joules per gram per degree Celsius. So let's go ahead and set up this value. The heat exchange, the heat of experienced by the water, the heat change experienced by the water, is represented by Q equals C times M times delta T. The C is 4.184 joules per gram per degree Celsius. The mass is the 1,000 grams, 4 sig figs there, notice the decimal point. And the temperature change is 81.4 minus 21.5 degrees Celsius. If we do that subtraction portion of the problem, you'll get 59.9 degrees Celsius. And so if we do this multiplication problem, you should get 250,621.6 joules, according to the calculator. The grams cancel out the grams, the degrees Celsius cancels out the degrees Celsius. Of course, this is not the correct number of significant figures. We are limited, let's see, we've got 4 sig figs, 4 sig figs, 3 sig figs, so we're limited by the temperature in terms of sig figs. We need to round off after 3 sig figs. And we get the answer 251,000 joules. Now, this is the energy change associated with the water. Notice that this sign is positive. It's not written down here, but it's implied. This is a positive number. The water experienced an endothermic change. It absorbed energy. But we don't want to know about the water. The question is asking about the drink. What energy change does the drink experience? Remember, energy cannot be created or destroyed. Any energy gained by the water must have been lost from the chemical reaction, must have been lost by burning the drink. So the energy change associated with the drink is equal in size but opposite in sign to the energy change experienced by the water. So we have negative 251,000 joules as the energy released by burning the drink. Notice the negative sign, which we associate with exothermic reactions. So we can double check to make sure that our answer makes sense. If it's exothermic, we know that the Q value should be negative.